we are going to talk about the stationary charges in electrostatics and dielectrics. Now let us see how we talk about stationary charges in electrostatics. So the dielectrics, some examples here are glass, wood, stone, water, plastic, wax, rubber. Now they are insulating materials or non-conducting materials. They can be polarized. They can be polar or non-polar. Both polar and non-polar, under the influence of external electric field, develop a net dipole moment. So we have a polar dielectric. As the name suggests, it has poles. So that's the symbol of a polar molecule. Example HCl. You have the dipole moment from the negative chlorine to hydrogen positive. Then another example of water, H2O, where oxygen is negative, hydrogen is positive, P is directed from negative to positive. What we see is the center of mass of the positive charge protons and the center of mass of negative charge electrons, they do not coincide. The molecules are asymmetric in shape. They have permanent dipole moments of the order of 10 raised to minus 30 coulomb meter. The charges are separated by a small distance, hence they act as a dipole. Other examples are water, alcohol, ammonia, etc. For water, angle is 105 degrees. It has high dipole moment of 6.1 into 10 raised to minus 30 coulomb meter. Then what are non-polar dielectrics? As the name suggests, they do not have poles under normal conditions. So it is represented like that. Let us take the example of carbon dioxide and the hydrogen molecule. In carbon dioxide, the center of mass of the positive charged protons and the center of mass of negative charges electrons, they coincide. Now in both of them, their molecules are symmetric in shape. They have dipole moment 0 in the normal state. Other examples are oxygen, nitrogen, methane, benzene, etc. Now let us see what happens when they are placed in an external electric field. When a non-polar molecule is placed in an external electric field, they get polarized. So when E0 is 0, they are not having dipoles. The moment an electric field is applied, these cling around and form the dipoles. The positive and the negative charges, they separate out, they are pushed away from each other, but there is always a tendency to come back. So there arises also a restoring force. So this continues. When an external field is applied, the displacement of the charges will stop. When the force due to the external field becomes equal to the restoring force between the charges in the molecule. Now the same way, when a polar molecule is applied electric field, they are already having poles, but due to thermal energy, these poles are not aligned. They are in any random direction. The moment an external electric field is applied, they cling around and they are aligned in the direction of the electric field, the external electric field. Thermal energy thus randomizes the orientation of the dipoles. The external electric field aligns the dipole in the direction of the field. Now, polarization is defined as the dipole moment per unit volume. For isotropic linear dielectric, polarization P is equal to psi into E, where psi E is the constant called electric susceptibility of the dielectric medium, which describes its electrical behavior. It is different for different dielectric. For vacuum, psi E is 0, so P is also 0. So, let's see how the electric field is reduced due to the polarization of the dielectric. So, we have a dielectric placed in the electric field, external electric field, as shown. The moment this electric field is applied to the dielectric, the positive and the negative charges, they separate out, they form dipoles and they are aligned in the direction of the field. So dipoles get aligned when a dielectric is placed in an external field, and they have a net electric field inside E naught. So you have positive charges here, the negative charges, and the electric field E naught reverse in direction to E vector. The sheets of induced surface charge produces electric field. So E naught is called polarization field of insulator. Now, when we are having E naught as the field inside, the net field is E dash. So we have the polarization field is E naught, which is developed inside due to the induced surface charges. Due to the external electric field, the charges move in the dielectric to a distance less than an atomic diameter. The magnitude of the net electric field E vector E dash is equal to E vector minus E naught vector. The induced electric field is responsible for the charge comb. All of you might have here seen the example of a comb. When it is rubbed against your hair, it can pick up bits of paper which are uncharged. This is due to this kind of an induced electric field. The induced dipole moment disappears when the field is no longer there. Dielectric constant of air is 1 and that of conductor is infinity. Minimum and maximum dielectric constant of paper is 1.5 and 3, and there are numerous examples. Next time we are going to see the use of this kind of polar and non-polar molecules, the dielectrics. So we'll continue next time. Bye.